In this lecture, we are going to discuss undecidability. So there are strict limits to what computers can do, and certain problems are beyond the reach of any computer and will be forever. And these problems are called undecidable. It's impossible to write a program that solves these problems. This is the subject of the lecture today. A decision problem P, that's something that we would like to answer via a program. So we would like to decide whether the property P holds or not. A decision problem P is nothing else than a language over some alphabet sigma. So it's just a subset of all words over sigma. Why do we consider decision problems as languages? If we are talking to computer programs, then we always have to pass the input in a certain way. So we have to tell the program what we want to know, and that means that we have to write it down as some word that we can pass as an input to the program. So for instance, think about you want to write a program that tells whether a certain number is prime or not. Then you have to write the number down, for instance, over the alphabet 0, 1. So you write it down as a binary number, pass it as input to the program, and then the program tells you whether this number is prime or not. So such a decision problem P is called decidable if the language P is recursive. And otherwise we say that the problem is undecidable. We say that the decision problem P is semi-decidable if the language P is recursively enumerable. So intuitively we can think about it as follows. The decision problem is decidable if there exists an algorithm that always halts and always answers yes or no. So there's an algorithm that we can give any word over sigma, and this algorithm will always stop and tell us whether this word is in P or not. A problem is semi-decidable if there exists an algorithm that will eventually stop and answer yes if the input word is in P. But if the input word is not in P, then the algorithm may never answer and compute forever. And the problem is that if we have a semi-decidable problem and we want to know whether the property holds or not, if it holds, then eventually we will get an answer, but if not, then we don't know how long we should wait. You might sit 1 year in front of your computer and you still don't have an answer, and you don't know whether it will never answer or maybe it will answer in the next 5 minutes. So with a semi-decidable problem, in the case that it does not hold, we can never be sure. A decision problem P is decidable if and only if the following holds, namely if P is semi-decidable and the complement of P is also semi-decidable. This follows simply from the definition of recursive languages, namely P is decidable if and only if P is recursive, and the definition of recursive languages says that the language is recursive if the language is recursively enumerable and its complement is also recursively enumerable. Intuitively, we can understand this as follows. If we have an algorithm that is a semi-decision procedure for P, and we have an algorithm that is a semi-decision procedure for the complement of P, then we can make from it an algorithm that always halts and tells us whether P holds or not by simply running the two algorithms in parallel. One of these will eventually answer, so P will always eventually halt. The most famous instance of an undecidable problem is the halting problem. And the halting problem asks the following. It asked whether a given Turing machine will reach a halting state eventually for a given input word. So the input of this problem are the Turing machine and the input word, and the question is, will the machine M eventually halt when given input W? This problem is not decidable, but it is semi-decidable. And it's very easy to see that it's semi-decidable because we can simply simulate the machine M on the input W and we wait. If it halts, we will eventually see it and we can answer yes. But if not, if it computes forever, then we can never be sure how long we have to wait. The following problem is not even semi-decidable. So it's undecidable and not even semi-decidable. And also the complement of this problem is not semi-decidable. It's called the universal halting problem. So it's also about the halting problem for Turing machines, but not for a single input word, but now for all input words. So it asks whether a given Turing machine M will reach eventually a halting state for every input word over the input alphabet sigma. So here the input is just the Turing machine. So we have said that decision problems are languages. So let's be a bit more precise about the halting problem and what language it corresponds to. So again, intuitively the halting problem means the following. We want to write a program that takes as input a Turing machine and a word X, and it answers us the question whether the Turing machine M will reach a halting state when given input X. So we can view this question as a language as follows. So we can view this halting problem as a language H. It consists of the pairs MX, for which the machine M reaches a halting state on input X. And formally, we don't put a real Turing machine here. Formally, we put a description of this Turing machine as a word in this place. So H is a language, and now the question is, can we write a program that decides membership in this language? So can we write a program that answers yes if a given pair is in the language and no otherwise? And the theorem is that this is not possible. The halting problem H is undecidable. The language H is not recursive. There is no deterministic Turing machine that takes an input and always reaches a halting state and answers yes if the word is in the language H and no otherwise. We've already discussed that this problem is semi-decidable, so we can write a program that answers yes if it's in, but we may have to wait forever and never see an answer no. So this problem is semi-decidable. The halting problem is really hugely important, and therefore we will give two proofs that it is undecidable. Let's start with the first proof. For contradiction, let's assume that the halting problem was decidable. So we assume that there exists a Turing machine H, I will refer to this as Oracle Turing machine, that on the input of a pair MX decides whether M halts on X or not. So it will answer yes or no. We will show that then every recursively enumerable problem would be recursive. And we have already seen that there are recursively enumerable problems for which the complement is not recursively enumerable. Thus, if we can show this fact, then we have a contradiction. So let M be a deterministic Turing machine. So M is now any Turing machine. In principle, it doesn't need to be deterministic, but we have already argued that non-deterministic Turing machines are equally strong as deterministic ones. So let's assume M is a deterministic Turing machine. And now we have a word X, and we want to decide whether X is in the language of M or not. If we can show that this is decidable, then it means that this language of M is recursive. And since M was arbitrary, it means that every recursively enumerable language would be recursive. So now let's give an algorithm for deciding membership of X in the language of M. How does it work? First of all, we ask our oracle machine whether the machine M halts on input X. And if our oracle answers yes, M halts on input X, then we are simply going to run the machine M and see whether X is in the language or not. And if our oracle machine says no, M does not halt on input X, then we know immediately that X is not in the language of M. So we can immediately stop and say, no, it's not in the language of M. So our algorithm for deciding membership will terminate in each case. Therefore, we have a decision procedure for deciding whether the word X is in the language of M. So since we have a decision procedure, this means that the language of our machine M is recursive. But this means that every recursively enumerable language would be recursive. So we have a contradiction. Our assumption must have been wrong. The halting problem is not decidable. Let's have a look at a slightly different proof of undecidability of the halting problem. The second proof that we are going to look at uses transformations of programs. Assume that the halting problem would be decidable. So there exists a program that takes as input a program and an input, and it decides whether the program terminates when given this input. Then we could also make a program T with the following behavior. It takes as input a program M, and it decides whether M terminates on input M or not. The program T is a special case of the program that decides the halting problem. Instead of deciding whether M terminates on some input X, T just decides whether M terminates on input M. So the input, instead of an arbitrary input X, is now just the program M itself. So if we would have a program deciding the halting problem, we could easily make a program T from it. So now let's assume that such a program T exists. It has abstractly such a form. It reads somewhere the input and somewhere it prints the result. Now we are going to change T. We are going to extend it into a program T prime. And this program T prime does not stop where the result is printed, but it continues and it checks. If the result of T is yes, then we are going to loop forever. And if the result is no, then we're going to terminate. Now what's going to happen if we run the program T prime on T prime itself? So we run T prime on input T prime. Now this first part, the program T, it's still the first part of T prime, this will decide whether T prime terminates on T prime. And if the answer is yes, T prime terminates on T prime, then T prime will actually loop forever. So if the answer is yes, then T prime loops forever. This is a contradiction. And if the answer is no, so if the program T says that T prime does not terminate on T prime, then what T prime actually does is it terminates. So this is also a contradiction. In each case, the program T prime does exactly the opposite of what the program T tells it does. If T tells that T prime terminates, then it does not. If T tells that T prime does not terminate, then it terminates. So what this means is that our program T must make a mistake. It does not correctly predict whether T prime terminates or not. So the program T cannot exist, and this means the halting problem is undecidable. The Theorem of Rice is very useful when reasoning about recursively enumerable languages. It tells us that every non-trivial property of recursively enumerable languages is undecidable. A property of a class K is said to be trivial if the property holds for all elements of K or the property holds for no element of K. So if you have a property that holds for some elements and it doesn't hold for other elements, then this property is non-trivial. The Theorem of Rice says that every non-trivial property of recursively enumerable languages is undecidable. So here we implicitly assume that the recursively enumerable language is given in the form of a Turing machine. So now let's prove the Theorem of Rice so that P be a non-trivial property. Without loss of generality, we may assume that P holds for the empty language. If P would not hold for the empty language, then we can do the same argument with the property negation of P. Because the negation of P is again non-trivial, and the negation of P is decidable if and only if P is decidable. So let's assume that P holds for the empty language. Since our property P is non-trivial, there's also some language for which the property does not hold. Let's call this language L0. So L0 is a language for which the property P does not hold. So P holds for the empty language, but P does not hold for L0. Now let L be an arbitrary recursively enumerable language. We are going to show that we can decide membership in L. And if we can decide membership, it means that L is recursive. But since L was arbitrary, it means that every recursively enumerable language would be recursive. And we already know that this is not the case, so this would be a contradiction. So how can we decide membership in L? We are going to construct a Turing machine, MX, that behaves as follows. So MX gets as input a word Y, and then MX does the following. First, it checks whether X is in L. So L was recursively enumerable. We assume that we have a Turing machine for L. So we can simply run this Turing machine and we see whether X is in the language L. And if so, if this is accepted, then we start a second Turing machine, namely the Turing machine for L0, and we check whether the input given to MX is in L0. So this first part here, this first check whether X is in L, this is actually independent of the input given to Y. So only if this Turing machine halts and says yes, then we are going to check whether the input Y is in L0. So what does this mean? It means that we get the following. If X is not in L, so if the Turing machine for L does either say no or never halts, then this first part here will always fail. It might run forever. But then the language accepted by MX will be empty. So if X is not in L, the language accepted by MX is empty. If X is in L, then eventually the Turing machine for L will accept, will say yes. And then we run the second check, namely whether Y is in the language L0. So then if X is in L, then this check will always succeed. So the language accepted by MX is then the language of all words in L0, so the language L0. So if X is in L, then the language of MX is the language L0. So now we see that if X is not in L, then the language of MX is empty. If X is in L, then the language of MX is L0. And we can decide, by assumption, the property P. We know that P holds for the empty language, but P does not hold for L0. So by deciding whether the property P holds, we know whether we have this case or we have this case. So we have that X is not in L if and only if P holds for the language of MX. So P holds for the empty language. So if P holds for the language of Mx, then X is not in L. And if P does not hold for the language of Mx, so this is the case for L0, then X is in L. So by deciding whether the property P holds for the language of Mx, we can decide whether X is in L. But this is a contradiction, because then decidability of P would mean that the language L is recursive. We can decide membership in L. So in particular, the theorem of Rice implies that the following simple questions are undecidable for recursively enumerable languages L. We cannot decide whether the word A is in the language. This property holds for some languages contain A, others do not, so this is not a trivial property, so by the theorem of Rice, this property is undecidable. We can also not decide whether the language is finite. Some recursively enumerable languages are finite, others are not, so this is not a trivial property, therefore undecidable by the theorem of Rice. Next, we are going to use the halting problem to show that many other problems are undecidable as well. And one very nice problem, which reminds a bit of a puzzle, which will also help us later to show that problems about languages are undecidable, is Post-Correspondence Problem. The Post-Correspondence Problem, short PCP, has been invented by Emil Post. And Emil Post is also one of the big figures in computability theory. He has contributed a lot to the foundations. The Post-Correspondence Problem is a very nice puzzle where we are given n pairs of words. So we have pairs of words w1v1, w2v2 up to wnvn. And the question is, can we pick a sequence of these pairs, and we can pick each pair as often as we want. We can use the first pair 10 times if we want. Can we pick a sequence of these pairs such that if we concatenate the left entry in each pair, we get the same word as when concatenating the right entry of each pair. So formally the question is, do we have indices I1, I2 up to ik? So these i's, they are numbers between 1 and n. Can we pick such indices such that the concatenation of wi1, wi2 up to wik is the same as the concatenation of vi1, vi2 up to vik? So if you think of these pairs as dominoes with the w above the v, then it means, can we put these dominoes horizontally next to each other such that the upper part of the dominoes reads the same word as the lower part of the dominoes together. So let's have a look at an example. Here we have a post-correspondence problem consisting of 3 pairs. Which pair should we choose first? We cannot start with the first pair because we would immediately have a mismatch in the first letter. It starts with a 0 on the left entry and the 1 on the right. Doesn't go together. Likewise, we cannot start with the second pair. But we can start with the third pair. So let's do so. We start with the third pair. We have 1, 1, 0 and the other entry is a 1. So I'm now writing the left entry on top and the right entry on the bottom. So the question is now, what pair do we pick next? We could continue with pair 1. Then we would have a 0, 1 on the top, the left entry, and we would have a 1, 0, 0 on the bottom, the right entry. If we concatenate them, it still matches up to now. So this looks quite good. We cannot continue with the second pair, because the second pair starts with a 0 in the right entry. This would immediately make a mismatch with this 1. So the second pair cannot be used at this point. Could we continue with the third pair? Let's have a look. The third pair is 1, 1, 0 and 1, and this also matches up to now. So we could continue with the first pair or the third pair. Now I know what the solution is, so I know it's good at this point to continue with the third pair, but you may also try to continue with the first and see whether you get to a solution. So let's continue from here. With what pair can we continue at this point? We need something that starts with a 0 in the right entry in order to match this 0 that we have here. So what pair starts with a 0 in the right entry? There's only one. Only the pair number 2 starts with a 0 in the right entry. We cannot pick pair 1 at this point, and we can also not pick pair 3. They would immediately yield a mismatch. So let's continue with pair number 2. Then we have a 1 and we have a 0, 1, 1. Now let's have a look that this still all fits together. And indeed, it fits still. So the next letter that we have to match is we need again a pair with a 0 in the second entry. So we have to again pick pair number 2 at this point. So let's again pick pair number 2. We get a 1 again and we get 0, 1, 1. Now let's have a look. On the top we are reading 1, 1, 0, 1, 1, 0, 1, 1. On the bottom we are reading 1, 1, 0, 1, 1, 0, 1, 1. So the concatenation of the entries on the top, the left entries of the pairs, and the concatenation of the right entries of the pairs is the same word. So picking the pairs 3, 3, 2, 2 gives us a solution to this post-correspondence problem. So we have found a solution, and this looks like a quite simple puzzle. So we would expect that a computer can solve such a puzzle, but actually we are going to show that this is impossible. It's not possible to write a program that solves all instances of the post-correspondence problem. It's undecidable whether a given post-correspondence problem is solvable or not. In order to prove that the post-correspondence problem is undecidable, we will do one small intermediate step. We are going to first prove that the modified post-correspondence problem is undecidable. It's almost the same as the post-correspondence problem, but it has one additional rule. It says that you have to start with the first pair. So we are not free in choosing any sequence of pairs. We have to first pick the first pair and then continue with an arbitrary sequence of pairs. Otherwise, the rules are the same as for the post-correspondence problem. We are still asked to find some sequence where the left entries concatenated gives the same as the right entries concatenated. We are now going to prove that the modified post-correspondence problem is undecidable. We're starting with an unrestricted grammar G. Unrestricted grammars give rise to the class of recursively enumerable languages. Membership in an arbitrary recursively enumerable language is not decidable. And we are going to show that if the modified PCP would be decidable, then also membership in this unrestricted grammar G would be decidable. So how are we going to decide whether the word W is in a language generated by G? We are going to define a modified post-correspondence problem in such a way that this modified PCP has a solution if and only if the word W is in the language generated by our grammar G. So how does this modified PCP look like? It consists of these pairs. So these pairs are now written horizontally. the left entry of the first pair is W1, the right entry is V1, the second pair is W2, V2, and so on. So the first pair, that's the pair that we have to start with, looks as follows. The left entry is F, the right entry is Fs arrow. The second pair, the left entry is arrow WE, so W is the word that we want to know whether it's in the language of the grammar or not, and the right entry is just E. Then we have pairs XY for every rule of our grammar X arrow Y. So for every rule X arrow Y, we have a pair XY in our modified PCP. We have pairs AA for every terminal letter A. We have pairs capital A for every variable A. And we have a pair arrow arrow. Now, this modified PCP has this property, namely that it has a solution if and only if this word W is generated by the grammar, but this is much easier to be understood by means of an example, which we will see on the next slide. So on the next slide we will see an example, and then it will become clear how this works. So for the moment you have to just believe that this property holds, and then we have a contradiction, because if the modified PCP would be decidable, then we could decide membership in an arbitrary unrestricted grammar, and that's not possible in general. Let's have a look at an example. Here we have a grammar, and we have a word AAAB, and we want to know whether the word is generated by the grammar. And we want to do this by translating this question into a modified PCP. So we use the translation that we've just seen. So we get a modified post-correspondence problem with 12 pairs. The first pair is the pair consisting of left entry F, right entry Fs arrow. The second pair is arrow AAAB, that's the word we are interested in, and then an E, and the right entry is an E. Then we have 4 pairs that correspond to our 4 rewrite rules of the grammar. So for instance, we have a grammar rule S rewrites to AA. Therefore we have a pair with left entry S and right entry AA. Then we have pairs. We have a pair arrow arrow. We have a pair AA for the terminal letter A, BB for the terminal letter B, capital A for the variable A, the same for the variable B and the variable S. So this is our modified post-correspondence problem, and the theorem says that this modified PCP has a solution if and only if this word AAB is in the language generated by the grammar. So let's have a look. The word is generated by the grammar, so we should be able to find a solution of this modified PCP. So we have to start with the first pair. So the left entry is an F, the right entry is Fs arrow. So we put the left entries we write on top, the right entries on the bottom. So this is our situation after having used the first pair. Now the idea is, of course, that we will try to model the derivation of the grammar in this modified PCP. So what happened in the first grammar step? The S was replaced by AA. So we should try to do the same kind of in the modified PCP. So we are going to use the pair that corresponds to the rule that we've used in this rewrite step, S rewrites to AA. This corresponds to this pair. We are going to put an S on top and AA on the bottom. So now you see that we have modeled the rewrite step. We had started with an S, and we have now derived AA. This arrow we can simply copy using pair number 7. So now the question is, what do we do with AA? We look again what did we do in the derivation of the grammar. The A has been replaced by terminal A variable B. So this is this rewrite rule, and this corresponds to pair number 4. So we are going to put an A on top and the terminal A variable B in the bottom. The second A has been left untouched, so we will do the same with the second A here. We will use the pair number 10 to leave it the same. Now we have an arrow which we again copy using the pair number 7. So now we have derived the word that was in our derivation also after 2 steps. Now what happened in the third step? The terminal A is just left unchanged, so we use pair number 8 to copy the terminal A. The variable B is also left untouched, so we will just copy this B using rule number 11. Now this variable A has been replaced by variable B terminal B. So using this rule, and this corresponds to this pair of our modified PCP. So we are going to use pair number 5. We put an A on top and the variable B terminal B in the bottom. We again copy the arrow using pair number 7, and we see that we have derived ABBB. So we have derived this word in our derivation with the grammar. The terminal again we copy using rule number 8. Now this variable B has been replaced by terminal A using this rule corresponding to pair number 6. So we will put BB on the top and terminal A in the bottom. This terminal letter again we just copy using pair number 9. And now we are done with the derivation of our grammar. We have AAAB. This is the word that we wanted to derive. So now we can use pair number 2 in order to finish. We put arrow AAAB E on top and an E on the bottom. And now the top row reads the same as the bottom row. So we have found the solution for our modified PCP. And in general, if we use this translation from grammars to the modified PCP, then it will always hold that the modified PCP has a solution if and only if the word that we put here in the pair 2 is generated by the grammar. The idea is that if we have a solution of the modified PCP, then from this solution we can read off a derivation in the grammar, just as we've done now, simulate the grammar derivation using the modified PCP. So now we know that the modified PCP is undecidable, and we're going to use this to derive that also the PCP is undecidable. So we start with an instance of the modified PCP. We have given n pairs, and we want to show that we can transform these pairs into an PCP instance in such a way that the PCP has a solution if and only if the modified PCP has a solution. So from these n pairs of the modified PCP, we are going to create n plus 2 pairs in our PCP. So these pairs are derived as follows. We start with the original pairs of the modified PCP, and for the left entries, we are going to insert dollar symbols after each letter. So the @ the dollar, and the hash are fresh symbols now. So for every left entry of a pair, we insert dollar symbols after each letter. For every right entry of a pair, we insert dollar symbols before each letter. So now these are out of sync, the dollars after the letter or the dollars before the letter. So that means we cannot start with these pairs, and we can also never end with these pairs. So we have one special pair that we can start with. it starts with an @ symbol, then it starts with a dollar, and then continues like pair 1 that we've already defined. So the extra dollar makes sure that we now also have dollars before each letter in the left entries. But now we have in the left entries an extra dollar. So this is basically, if we are concatenating pairs now, then the left entries will always have an extra dollar in the end that is missing from the concatenation of the right entries. So in order to finish, we have to use a pair of this form where we add this extra dollar at the end of the concatenation of the right entries. So we cannot start with these pairs, we have to start with these pairs, and that's a modified version of pair number 1. So this basically means we have started with pair number 1. Then we can use these pairs, and then we have to end with a pair of this form. So any solution of our post-correspondence problem always must start with pair number 0 and must end with pair n+1. So from such a solution we can always reconstruct a solution of our original modified PCP, and we can show that the PCP that we have has a solution if and only if the original modified PCP has a solution. And from this we may conclude that the PCP is undecidable, because if it would be decidable, then we could also decide the modified PCP. So here we have an example of this transformation. We have given an instance of a modified PCP and we transform it into a PCP. So this is our first pair of the modified PCP. We transform it into PCP. We insert dollar symbols after each letter of the left entry of the pair. So we have a dollar after the one and a dollar after this one. We insert dollar symbols before each letter in the right entry of the pair. So this gives dollar before this one. We do the same with this pair. We insert dollars after each letter in the left entry. So it gives $1. And dollars before each letter in the right entry. So this gives $1, $1. Now, we cannot start with these pairs. They are out of sync. The dollar mismatches with the 1, and we have also here a mismatch. We have one additional pair 0, which is basically a modified version of pair 1, and it's modified in a way that we can start with this one. We have this additional @ symbol in front, and we add one more dollar in front of the left entry of pair number 1. By adding this additional dollar here, now we are in sync and we can start with this pair. And we have one additional pair to finish, because now the left entries always end with a dollar, the right entries not. So the only way to finish is if we add a dollar to the right entries, and then we can stop. So now let's have a look how a solution translates. We have for this modified PCP, we have a solution by picking pair 1 and then pair 2. If we pick pair 1 and then pair 2, then the concatenation of the left entries gives us 1, 1, 1, and the concatenation of the right entries also gives us 1, 1, 1. Now this solution corresponds to a solution of our PCP. Instead of using pair number 1, because we cannot start with pair number 1 here, we have to start with this modified pair number 1, which is now called pair number 0. So we start with pair number 0, then we continue with the translation of pair number 2. So this is the pair number 2 that we continue with of our PCP. And then we have to finish with this additional pair 3 to put the dollar in the end of the right entries. So we pick pair 0, 2, 3, and this gives us this solution of our PCP. And if we ignore the fresh symbols, the @ the dollar, and the hash, then we see that this is exactly a solution of our modified post-correspondence problem 111. So this holds in general, this modified PCP has a solution if and only if the resulting PCP has a solution. Now we are going to use undecidability of the post-correspondence problem in order to establish that various properties of context-free languages are undecidable. In particular, we are going to establish that emptiness of the intersection, ambiguity, palindromes in the language, language equality, that all these are undecidable properties of context-free languages. We are going to prove now that the problem of emptiness of the intersection of context-free languages is undecidable. So for context-free languages L1 and L2, given in the form of context-free grammars, it is not decidable whether they have an empty intersection or not. And in order to prove this, we are going to use a problem that we already know is undecidable. We are going to use the post-correspondence problem, and we will reduce it to the question of emptiness of the intersection of context-free languages. And then if this question would be decidable, then we would also be able to decide the PCP, and this would be a contradiction. So let's start with an instance of the PCP. We are given n pairs of words, w1v1 up to wnvn. And now we are going to construct grammars, g1 and g2, in such a way that their languages intersect if and only if this PCP instance has a solution. The grammar G1 contains the following rules. It contains 2 rules for every pair in our PCP. So for every I between 1 and n, we have these 2 rules. We have a rule from the starting variable s1 to wi s1 and an I in brackets, or to wi hash and I in brackets. The hash and the brackets are fresh symbols. So we can, from the starting variable s1, we can produce left entries of the pair, s1 again, and then the index I in brackets. Or we can just produce one left entry, put a hash in the middle, and the index, and here's no variable s1, so if we use this rule, then we stop. Now, the grammar G2 can basically do the same, but instead of left entries of the pair, we produce right entries of the pair. Now, what words can we generate from these languages, from these grammars? The languages are as follows. The language of G1 consists of words of this form. We have to stop with this rule, so we have a hash in the middle. And right of the hash we have indices in brackets, and left of the hash we have a concatenation of left entries of our pairs. The grammar G2 generates words of this form. We have a hash in the middle, right of the hash we have indices in brackets, and left of the hash we have concatenations of right entries of the pair. Now, when do these 2 languages intersect? When is a word in both of these languages? The hash appears only once, so the hash has to match, and then these indices on the right have to match. So these indices have to match. It means that we basically pick, for both grammars, we pick the same indices in the same order. And since we pick the same indices in the same order, it means that we get, for the first grammar, we get a concatenation of the left entries of these indices. And for the second grammar, we get a concatenation of the right entries for the same indices. So this matches only if we have found a solution of our post-correspondence problem. So these 2 languages intersect if and only if the post-correspondence problem has a solution. So if we could decide emptiness of the intersection, we could decide whether the PCP that we started from has a solution. And since we know that this problem is undecidable, the question about intersection of context-free languages must be undecidable as well. Next, we are going to show that ambiguity of context-free grammars is undecidable. The proof is basically almost the same as the proof that we've just seen. We start with a post-correspondence problem. So we take an instance of the PCP and we reduce it to a grammar. Now, the right part here is basically the same as we just had on the last slide. We have our grammar G1 and our grammar G2. Now we put these two grammars together in one grammar and we add a fresh starting variable and two new rules, namely the fresh starting variable can rewrite to S1 as well as to S2. So we can either generate a word from S1 or from S2. Now we have already argued on the last slide that these two grammars, or these two variables S1, S2, they generate the same word if and only if the post-correspondence problem has a solution. So that means that we have ambiguity, namely S1 generates a word, the same word as S2 generates, if and only if this PCP has a solution. It's not difficult to check that indeed we do not have any other source of ambiguity. The main idea is that this index that we include here makes clear what rule we've chosen. So we don't have any ambiguity purely coming from S1 and we don't have any ambiguity purely coming from S2. The only source of ambiguity is from this choice if S1 and S2 generate the same terminal word. So if the language of S1 and the language of S2 have a non-empty intersection. So as a consequence, the grammar G that we've defined is ambiguous if and only if the post-correspondence problem that we started from has a solution. And we know that this is undecidable, therefore ambiguity of context-free grammars must be undecidable as well. It is also undecidable whether a context-free language contains a palindrome, so a word W that is equal to its own reverse. We again use the post-correspondence problem. We start from an instance of the PCP with n pairs. We have pairs W1, V1, W2, V2 up to Wn, Vn. And now we define a context-free grammar as follows. For every pair we have two rules in the grammar. From our starting variable s we can rewrite to Wi s Vi reverse or to Wi hash Vi reverse. And the hash is again a fresh symbol. So by applying instances of this left rules, we concatenate Wi's on the left, and at the same time we concatenate Vi's in reverse on the right. We finish by putting a hash in the middle, and now when is such a generated word equal to its own reverse, so when is it a palindrome, it means that the concatenation of the Wi's that we had created in the left must be equal to the reverse of the concatenations of the Vi's in the right. And this is equivalent to the post-correspondence problem that we've started from having a solution. So this language contains a palindrome if and only if the post-correspondence problem has a solution. Since this problem is undecidable, also the question about palindromes must be undecidable. Finally, we are going to show that the question of language equality for context-free languages L1 and L2 is undecidable. And even the particular instance of this problem asking whether a context-free language is equal to the language of all words over the alphabet sigma is also undecidable. So this is an instance of the more general question. If we show that this instance is undecidable, it follows that also the general question is undecidable. So let's start with the proof. We again start with an instance of the post-correspondence problem, and we start with a grammar or two grammars that we've already constructed when we've considered the emptiness of the intersection of two context-free languages. So we had already constructed these grammars G1 and G2, and they had the following nice property, namely that the post-correspondence problem has no solution if and only if the intersection of the languages of G1 and G2 was empty. So this we've already proven before. Now we take the complement on the left and on the right. So if we take on both sides the complement, we get that this is equivalent to the complement of the left being equal to the complement on the right. The complement of the empty language is the language containing all words over sigma. And the complement of the intersection of the language of G1 and the language of G2 is equal to the union of the complements of G1 and the complement of G2. Now, this is already in the form of our question. In our question, we wanted to have the left-hand side as a context-free language. So we have to show that the left-hand side is a context-free language. We know that the union preserves context-free languages. So it suffices to show that the complement of the language of G1 is context-free and the complement of the language of G2 is context-free. But G1 and G2 are defined analogously, so actually it suffices to show it for one of them, and for the other one it follows in the same way. So now it suffices to show that the complement of the language of G1 is context-free. And then because we know that this is undecidable, it follows that this question must be undecidable, and therefore these problems are indeed undecidable. So we will continue by showing that the complement of the language of G1, of this grammar, is context-free. This is our grammar G1, and all the words generated by this grammar are of this form. We have some word over sigma on the left of the hash, then we have a hash, and then we have indices in brackets, and these indices are numbers between 1 and n. So all the words generated by G1 are of this form. Some word over sigma, a hash, and then some concatenation of indices in brackets. So this language ls obviously is a regular language. So now we can reason as follows. We know that everything generated by the grammar G1 is of the form of the words in ls. So now let's reason about the complement of the language of G1. The complement of the language of G1, just by definition of the complement, is all words over sigma minus the language of G1. So this is just by definition of a complement. Now, sigma star we can rewrite in a different way. We can write sigma star as the union of the language ls with the complement of ls. If we take any language, union its complement, it will give us all words over sigma. So this is equal to this expression. Now we know that every word in the language of G1 is of the form ls. We have that the language of G1 is a subset of ls. So this means that none of the words in the language of G1 are in the complement of ls. So this language with the complement of ls has an empty intersection. That means if we take the union and then we subtract the language of G1, it means we don't take any words out of the complement of ls. All of these words that we take out, we take from ls. So we can equivalently write this in this form. We can say that this is equal to ls minus the language of G1 union the complement of ls. Now, ls is a regular language, therefore the complement is regular and thus also context-free. So what we have to show is that the left-hand side ls minus the language of G1 is also context-free, and then we know the union preserves context-free languages, then it follows that this language is context-free and thus the complement of the language of G1 must be context-free. So it boils down to showing that ls minus the language of G1 is context-free. And we are going to do this by considering 3 cases. So first of all, note that the words in the language ls minus the language of G1 are of this form. So ls minus the language of G1 is the set of all words of this form. So we have some word w over sigma star, followed by a hash, followed by some indices. So this is basically the shape of words in ls. And when are these words not in the language of G1? They are not in the language of G1 if the word that we have here on the left is not the concatenation of the words wi that correspond to the indices on the right. So this word is not in the language of G1 if w is not equal to the concatenation of wj up to wk. So this is this indices j up to k, and on the left we have then the concatenation of wj to wk. And if this word w is not equal to this concatenation, then this word is not generated by the grammar G1. So we are now going to show that this language is context-free. And the crucial observation is that we can split it into 3 languages. We know the union preserves context-freeness, so it suffices that each of these 3 languages is context-free. The first language, L smaller, is the language of those words where the length of w is smaller than the length of the concatenation of wj to wk. This is this language. The second language, L larger, is the language of all those words where the length of the word w is larger than the length of the concatenation of wj to wk. And finally, the language L equal is the language of all those words where the length of w is equal to the length of the concatenation, but they are nevertheless not the same. For each of these 3 languages, it is a nice small exercise to give a context-free grammar. And I leave this exercise to you. So try to find context-free grammars for each of these 3 languages. This implies then that these 3 languages are context-free. Since their union is also context-free, it means that the language of ls minus the language of G1 is context-free, and this was sufficient to show that our problem was indeed undecidable. At the end of this lecture, we are still going to have a small look at semi-decidability. Recall that a problem P is called decidable if the language P is recursive. So if there exists a Turing machine that on every input word over the alphabet sigma answers yes or no whether the input word is in P or not. A problem is called semi-decidable if there is a Turing machine that eventually answers yes if the given word is in P, but if the word is not in P, it may compute forever. So we've seen many problems of semi-decidable problems. So all these problems are semi-decidable, but not decidable. So they are still undecidable. The halting problem is an instance of a semi-decidable problem. The halting problem asks for a given Turing machine and an input word. Does the Turing machine halt on this input word? This problem is semi-decidable because we can simply run the machine on the input word and we wait until it halts. If it halts, we can eventually answer yes. But if it doesn't halt, then we may have to wait forever. The halting problem needs to be distinguished from the universal halting problem. The universal halting problem is not even semi-decidable. The universal halting problem asks for a given Turing machine. Does this Turing machine halt on every input word? So the universal halting problem is not semi-decidable, and also the complement of the universal halting problem is not semi-decidable. The post-correspondence problem is semi-decidable. Given an instance of the post-correspondence problem, we can write a program that simply tries every possible combination of the pairs of words, so it picks them in any possible order. If there is a solution, then we will eventually find the solution. But if the post-correspondence problem has no solution, then our program may search forever. Likewise, the non-emptiness of the intersection of context-free languages, we can write a program that takes two context-free grammars, and it simply generates all possible words that can be generated by the grammars. And if we find some word that is generated by both grammars, then we stop and say, yes, the intersection is non-empty. But if the intersection is empty, then our program will compute forever. It will search forever. The same for the ambiguity of context-free grammars. We can write a program that takes a context-free grammar and that generates all possible derivation trees. And if at some point we find two derivation trees for the same word, then we can stop and say, yes, the grammar is ambiguous. But if the grammar is not ambiguous, then our program will search forever. So all these problems are semi-decidable. We can make a Turing machine that takes an instance of the problem, and if the instance is a positive instance, it's in P, then we eventually answer yes. If the instance is a negative instance, then our Turing machine will compute forever. So we can, for these problems, not make a Turing machine that always halts and always answers yes or no. These problems are not decidable. These languages are not recursive. To conclude, I would like to mention that there are many famous problems that have turned out to be undecidable. So one of them we've already discussed is the validity of formulas in predicate logic. So it's impossible to write a program that takes a formula from predicate logic as input and tells whether the formula is true or not. It's not possible to make a program that always answers correctly for each formula. In 1900, David Hilbert has published 23 scientific problems that were all open at this time, so the solution was not known. One of these problems is about Diaphantine equations, so we have polynomial equations over integer coefficients. So the question is, given such a system of polynomial equations, is there an assignment of the variables that is a solution of the system, and the variables should be assigned with integers? This became known as Hilbert's 10th problem. So Hilbert has asked whether it's possible to decide whether there's a solution or not. And it was open for quite a while. In 1970, it has been shown that this is impossible. It's not possible to give an algorithm that solves this problem. It's not possible to write a program that solves this problem. This question of Hilbert is undecidable.